Hello, dear students, and welcome to another session with SJ or EduSphere. Today, we will explore the concept of linear regression. But, like we always say, let us not by heart but understand the concept. So, the initial process will have a recall of the correlation topic, and then we will derive the formula list for linear regression. So, watch it for application based question, drawbacks of this method, and where I can use linear regression in daily life. So, let us first recall what we've done in the topic correlation. Before that, when I have a set of data for any particular values of x and for any particular values of y, I can find my mean x bar, that is summation x upon n, and I can find my mean y bar, that is summation y upon n. Now, suppose I say I want to find the value for correlation. What have we studied? Correlation between x and y is covariance of x and y upon standard deviation of x into standard deviation of y. For that, let us derive standard deviation formula. Well, standard deviation, students, is the positive square root of variance. What is variance? Variance is your variation in the data from the mean value. How far are each value away from the mean value? We take the square of it, for which if I have my column of x and y, I will end up finding my variance of x is denoted as sigma x square, formula summation x minus x bar the whole square upon n, which can also be written as summation x square over n minus x bar square. Similarly, my variance of y over here can be written as sigma y square, that is summation y minus y bar the whole square upon n, which can also become summation y square upon n minus y bar square. Now, what have we derived? We have derived what is my variance of x and what is my variance of y. If I talk about my combined variance, what is covariance? Covariance of x and y is combined variance of x and combined variance of y. What happens there? In variance, both are x terms. In combined variance, one term will be x minus x bar, y minus y bar upon n, which can also be written as same way x square y square. So here you will have x and y upon n minus x bar y bar. Now students, can I write x bar as summation x upon n and y bar as summation y upon n? So if I take the LCM, will I have the denominator as n square, and here I will have n times summation xy minus summation x summation y. Pause. How did I get this? I simply wrote x bar as summation x upon n, y bar as summation y upon n. N and n became n square. So for LCM, I multiplied it over here. Similarly, can I write this formula for variance? X bar is summation x upon n the whole square. That will give me n summation x square minus summation x the whole square over n square. And similarly, this will be n summation y square minus summation y the whole square over n square. So when I come to my correlation value, what does my formula say? My formula says covariance divide by the standard deviation, means root of this answer and root of the second answer. Now, do you go out to by heart it? No. We are going to use a very simple trick to get this answer. We will focus on the numerator. Okay. So can I write my covariance over here as summation x minus x bar y minus y bar as the numerator in the first case. In the second case, can I write it over here as n times summation xy minus summation x summation y as my covariance. Now, for standard deviation of x and y, make two roots. First root for standard deviation of x and the second root for standard deviation of y. Read all the numerator for standard deviation of x, read the y as x. So x minus x bar over here again into x minus x bar gives me summation x minus x bar the whole square. And similarly over here, now read the x as y. So I will have y minus y bar into y minus y bar gives me over here y minus y bar the whole square. How did we get this? It is the green formula here with n in the denominator divided by the black formula here with n under root and over here with n under root. That gets cancelled with this n. Similarly, I am now taking the second formula with n square in the denominator, comparing it with this formula with n square under root and over here with n square under root. N square and n square under root will cancel with this term. So, if I only know my covariance numerator, I am going to read again all the y's as x. So, n summation x into x is x square minus summation x into summation x the whole square. Similarly, now read all the x's as y's. N summation y square minus summation y into y the whole square. This gives you your r. What is your property for r, students? Your r value is always between -1 to 1. That is, -1 less than equal to r is less than equal to 1. This is called as your coefficient of correlation. That means how strong is the bond between x and y. If I take r square, now if r is between -1 to 1, square of all negative will be positive and square of 0 will be 0. So r square will belong from 0 to 1. That is your coefficient of determination. That means what is the chance of it happening? Coefficient of determination. Now, keeping this concept in mind, keeping these two formulas in mind, we are going to derive the entire formula list for linear regression. Before that, what is linear regression? So, now linear regression in itself is a line. My general equation of a line is y is mx plus c, or y minus y bar is slope x minus x bar. So in correlation, you compare that with the change in the value of x, is there a change in the value of y? So for which we have a positive and negative answer, means if x increases and y also increases in the same direction, that means if your graph is going from bottom left to top right, or I can say with decrease on of x there is decrease of y, same direction, we call it as positive correlation. Similarly, if with the increase of x there is decrease in y, or with the decrease in x there is increase in y, your graph going from top left to bottom right, this is your negative correlation. What can be your examples over here? Can I say over here that when x suppose is the number of hours you study and y is your marks, The more hours you study, your marks go higher. Yes, there are special cases. Can I say in the negative correlation, if price of a product goes higher, the demand goes less? Okay, these are common examples. But can I say over here that when your temperature goes higher, the sale of cold drinks go higher? When temperature goes higher, your sale of ice creams go higher. When my dollar rate goes high, my crude price goes up. These are examples of positive correlation. Clear? Similarly, we go ahead that after knowing the relation for x and y, how can I predict them? So we've analyzed the data, we've got their strength, but what is the use if we do not predict values? That exactly comes over here in linear regression. So linear regression is equation of a line which helps you to predict the values. So there are two types of linear regression line. The first line that we have over here is y on x, and the second line that we have over here is x on y. Now, what do I mean by y on x? Y on x means y is dependent on x. That means in this particular case, if I want to write in a little simple language, over here x is given to you and y is asked. So I am telling you to find the value of y when x is given to you. Similarly, when I say x on y, I am saying x is dependent on y. X is dependent on y means knowing the value of y, that means y is given, you need to find x. Clear? So let us first break one part and then go ahead. Whichever kind of question do you have, students, your first step remains the same. In both the types, you will end up finding the mean. That means x bar is summation x upon n and y bar is summation y upon n. This gives you your mean value. Now, so over here you will have your column of x, you will have over here your column of y. I need my total of x, I need my total of y. Now, when I'm saying y on x, get the pattern. Y on x means first y, then x. So, I will say y on x. So, first y, then x, a. Y on x means b y x. What is b y x? B y x is your regression coefficient of y on x. Okay, so y on x, first y then x. Another equation is y minus y bar, x minus x bar. Y on x, pehle y fir x, and here I will have byx. So we need to find the value of x bar, y bar. How do I find byx? So everyone over here, go with the pattern. Y on x means covariance xy on variance of x. Well, the initial 10 minutes that we used was actually to find out this formula. We have covariance and standard deviation was the square root of variance. In this method, I am asking you the variance. That means this term over here will be without the root either x, either y, or this formula either x, either y without the root, which becomes your regression coefficient, students. So again, do not by heart. Can I say my numerator over here remains the same? I can use the first formula, summation x minus x bar, y minus y bar. You want y on x, so down you will only have the x term. Or if you use the second formula, n times summation xy minus summation x summation y upon, read all the y's as x. So n x into x, summation x into summation x, that is summation x the whole square. This is your formula for byx. Once you find this, you put it in the equation, you get your regression line of y on x. For this, what do I want? If I have x and y, my next column will be x into y, the total over here, and I need total of x square. This will be your total of x square. Putting these values, you get the answer. Similarly, I come over here for x on y. X on y, first x, then y. So my line will be first x, then y. So x on y will be a dash plus b, first x, then y. X on y, pehle x, then y. Here you will have bxy. So don't by heart. For that, I need to find bxy. Similarly, what is bxy? This is your regression coefficient of x on y. To find the value for bxy, can I write this over here as bxy is covariance xy on variance of y? Covariance remains the same. So your numerator formula will continue, which I'm writing in the same number for your explanation. So here I will have x minus x bar, y minus y bar. You want only on y. Read all the x's as y's, and you have y minus y bar the whole square. Similarly, keep the same formula. N times summation xy minus summation x summation y upon, I need only y. Read all the x's as y's. So n summation y into y is y square minus summation y into summation y will give you summation y the whole square. So what columns do you need in this sum? You have x, you have y, you need the total of x, you need the total of y. You will go ahead to find again the product of xy to get total of xy, but in this case this is x on y. You need a y square to get the total of y square. This is one set of formula when you are given datas of x and y. Now, do we remember all of this? No. Let's simplify the work. You need to remember the equation, know the parent formula, stick to this method. Remember the equation, know the parent formula, stick to this method. This is when I have my columns of x and y given to me. But what if I have direct answers given to me? So again, we derive that part. Everyone, look at what I have written. Have I said byx? If I say byx is covariance xy on variance of x, and if I say bxy is covariance xy on variance of y, if I multiply the students, will I have byx into bxy? Look carefully, is covariance of xy square. Variance was standard deviation of x ka square and standard deviation of y ka square. So this whole thing is under square. This was your formula for correlation. That means this is your r square. So when I multiply the regression coefficient, I get over here r square, that is my coefficient of determination. This over here is my coefficient of determination. Now everyone, if I want to find my correlation value. So will I say R is plus minus square root of byx into bxy? Now how do I decide the sign? Students, you know variance is always positive. Variance is always positive. That means the sign will depend only on covariance. The covariance is fixed for byx, for bxy, for r. That means if byx is greater than 0 and bxy is greater than 0, then r will be greater than 0. And if byx is less than 0 and bxy is less than 0, then r is less than 0, means all three hold the same sign, and that depends on covariance. Now look over here. Have I said byx? I'm writing it over here. Have we said that byx is covariance xy on variance of x? Students, can I write byx as covariance xy upon sigma x square? Can that be written as 1 standard deviation x over here and 1 standard deviation x over here? I am multiplying numerator with standard deviation of y and balancing over here with standard deviation of y. Well, this is your correlation. So my second formula becomes byx is r sigma y upon sigma x, and similarly bxy is r sigma x upon sigma y. Wait, before you start confusing yourself, do you by heart all this? No. Again, y on x, by on x is r standard deviation of y on standard deviation of x. Simple. Similarly over here, bxy is r standard deviation of x upon standard deviation of y. So if you directly have your data given to you for mean and direct calculation for variance or standard deviation, you can use this method and get to the answer. Clear? Now, what happens for the third method when you already are given a line? How do I identify which is x on y and one which is y on x? So suppose you have line 1 as a1x plus b1y equal to c1, and you have line 2 which is a2x plus b2y equal to c2. We will find the slope, that is minus the coefficient of x upon coefficient of y. So in this case, my slope is minus coefficient of x upon coefficient of y, and modulus of m1 is a1 upon b1. Similarly here, slope is minus coefficient of x upon coefficient of y, and my modulus of m2 is a2 upon b2. Now students, if modulus of m1 is less than modulus m2, whichever absolute value is less, then byx will be the original m1 and bxy will be the reciprocal of the original m2. Similarly, if I say if modulus of m2 is less than modulus m1, then byx is the original smaller value and bxy is the reciprocal of the original bigger value. This will help you to get the values of byx, bxy, and to identify which line is y on x and which line is x on y. Now, few parts to keep in mind. When I have my line of x on y and when I have my line of y on x, when I plot them on the graph, if I have L1 and L2 solved simultaneously, wherever they will meet is actually your x bar and y bar, because that is one common point which will satisfy both the lines because they are for the same set of data. Similarly, can I also say that byx and bxy is my geometric mean? When I get my correlation. So I am saying R is the geometric mean of my regression coefficients. Okay. Similarly, I am saying that with the rule which says that correlation has to be between -1 and 1, and with my coefficient of determination to be between 0 and 1, if any one value of byx and bxy is greater than 1, if any one regression coefficient is numerically more than 1, the other is numerically less than 1. That allows me to bring down their product between 0 and 1. So when you keep these properties in mind, you can easily solve the sum, identify the methods, and get your entire chapter sorted. So please get this table in place. Once you identify the table, once you know these set of tick formulas, you can solve any kind of sums and go ahead with linear regression. Know the properties because they are very important to get to the answer. One part what we can add over here is, if my value of R is 0, well, R is because of covariance xy upon standard deviation x and standard deviation y. Students, any value is 0 only when the numerator is 0. That means my covariance you got 0. If your covariance is 0, does that imply that byx and bxy also will be 0? So, will my line of y on x be y minus y bar is 0, x minus x bar? That means y is equal to y bar. And similarly, will my line of x on y be x minus x bar is 0? That means x is equal to x bar. If I go ahead to draw them on a graph, can I conclude this part with saying that y is equal to y bar? That means your line is parallel to x-axis. And similarly, when I say x is equal to x bar, the line is parallel to y-axis and both the lines are perpendicular to each other. So if your covariance is 0 or correlation is 0, byx bxy will be 0 and the regression lines will be perpendicular to each other. Further, if my value of R is perfect positive or it is perfect negative, then lines will coincide. That means they will be one upon the other line. So where can I use this in real life? Imagine a scenario where in your class 20 students have given your economics and mathematics paper. Economics is X, mathematics is Y. You gave your economics paper, but sadly you could not come for your mathematics paper. Can I analyze the data of those 19 students who have given X and Y both? Okay, So can I say you have given X, that is economics, and I want to find your value of Y, that is mathematics. So mathematics is depending on your economics performance. So I will find the line of Y on X. For those data, since they are your batchmates of the same school, of the same division, I can say the performance will be the same. And hence, with that, I will find the line of Y on X. For your given value of X, I can predict what will be your score in mathematics. In such scenarios, we use the linear regression. But what is the drawback? The drawback is we have considered your performance of maths based on eco alone. But is economics alone going to judge your performance in maths? Maybe that day you were not well, maybe some scenarios have come in place, or maybe economic concept have not been great with you. So there are multiple factors which actually lead to an output of a dependent variable. Here we are limiting our thought to two variable concept, where example we say crop yield depends on rainfall. But in real life, crop yield depends on rainfall, quality of soil, quality of seed, irrigation facilities, and multiple factors. We are limiting it to only one dependent factor, which is on one independent factor. In real life, there are more than independent factors. That is a multiple regression model. For now, we are understanding two variables and going ahead with the concept. So understand the concept, get it properly, share it with your friends to help them also learn this concept well, and do hit the like button if you like this lecture. Happy learning.